Does your olive oil have poison in it? Okay, that's not really what we're looking at too much, but it is in a sense. There's this pesticide, Fenthion, that's put on olive leaves, and the question is residue getting into olive oil? And if so, is it dissipating over time to the point where it's at levels that aren't hurting us, or does it kind of just stay strong once it's in that olive oil? So we've got three separate groups here. We can see this by the day number. This is when the Fenthion is first measured. This is after, I guess, the olive oil has been sitting 2/3 of a year or so, and then after it's been there a full year. And these are the amounts of Fenthion. So those are the two variables we want to look at here. The response, the thing that we're interested in, the outcome, the Y, WHY, or just the letter Y in terms of the axis of why we're doing all this, is the amount of Fenthion. That's what we're really concerned with. We want to see if that actually varies by the day. So the day would be our explanatory, Fenthion would be our response here. And this is good grounds for an ANOVA because we've got the days lumped into three different categories here. If we had a quantitative variable day, it would probably be more conducive to a regression. Okay, so we have these three different groups. Let's test out to see if we're meeting the assumptions. Okay, one thing we can do is start off with some plots in the descriptives. We're also going to need these descriptive statistics here in a second. So again, the level of Fenthion is what we're concerned with, but we want to split it by the day. This will split us into the three groups there. You can see across the top. And we have 6 data points within each of these three groups. And we have our sample means, sample standard deviations, low and high points, but we want to visualize it too. So if we go to plots, box plots, again, with this many data points, I think a box plot's a little bit silly. I think it's better to get the actual data there. And to be honest, I think it's nicer without the box plot to be able to see where the data points are. If we had a larger data set, these dots just get overwhelming, and then that's where the box plot is really nice. Okay, so we're looking at a couple of things here. The independent assumption, so the fact that each one of these data points doesn't impact the other ones, that's not something we can check visually, but based on the description they give us of how this data was collected, I don't think that any one of these data points is impacting the other. There's no dependency there. I would say that the data are independent. One thing we can see visually, though, is that the spread within the groups is different. So here they're fairly tightly clustered together, a little more spread out, and here there's even more variance. We can see that also in the standard deviations here if we look. So the way to look here, the rule of thumb, is taking the lowest standard deviation and the highest standard deviation, so in that case it would be the 0.06 and the 0.17, and we divide the highest by the smallest. So the 0.17 divided by 0.06, and that'll give us almost 3. It'll give us 2 point something, high twos. This is enough to pretty strongly warrant a violation of the equal variances assumption. So the rule of thumb there is you want this number to be less than 2. If you take the highest standard deviation divided by the lowest standard deviation, ideally, if that number is below 2, we're okay with assuming that the populations these are coming from have relatively equal variances, or essentially we're assuming that it has the same variance. There is another test, and I'll show you just in a second, that we can look at there. Could we go ahead and analyze these data as is? Yeah, I mean, it happens all the time, especially because, as we'll see in just a second, we do have a non-significant, it's not going to officially be classified as unequal variances, and I'll show you that in just a second. But in this problem, I think what we're looking at is potentially doing a transformation and seeing if we can get that variation closer together, those standard deviations actually closer together. So the next thing we'd like to do is, in part C, create a diagnostic plot. And this will let us know what kind of transformation do we do here. Do we just put all the Fenthion data, the log version of it? Do we do some kind of exponent? That's what this diagnostic will tell us. And there may be a way, if you find a way to do it using real quick technology, please let me know. The book gives a set of procedures here that I'm going to go through. And to do that, we're going to use the means and standard deviation data here. It's much easier to work with the data in Excel or Sheets, so I'm going to go ahead and copy that to the clipboard, open up Excel, and let me paste that data. I'll just paste it normally. So I did a Control V there, by the way. I'm going to make this a little smaller, perhaps. Okay, again, we want the log of the means and the log of the standard deviation. So what I'm going to do is say natural log of mean. That's going to be our x variable, and then we'll take the natural log of the sample standard deviation. And I could set up I kind of missed setting up a formula here. I'm just going to type these in, ln d6. If there was a lot more of these, I would probably do cut these to clipboard, do a paste special transpose, which would flip the XY axis, and it would let me run these formulas a little more simply. But since I only have 6 of them, I think it's honestly easier to do this. Just taking the natural log of all the means and the standard deviations. Okay, and now we have 3 data points, essentially XY data points, where we're going to insert a scatter plot, and then we're going to add a trend line, linear trend line, but we do want to display the equation on the chart because what we really want to know is that slope of this. So it does follow a straight line, which is suggesting that a transformation might be a good idea here. And the specific power of our transformation, so we're going to take all the Fenthion data to a certain power. What power would that be? It would be 1 minus the slope of the trend line we just found. The slope of the trend line we just found is negative 1.4. Excuse me. So that would be 1 minus negative 1.4, or 2.4. So our diagnostic here is telling us that maybe we should consider raising every data point in our data set to the power of 2.4. Now, we could go to the nearest power there, which would be to the power of 2, or squaring, not the square root, but we would square all the Fenthion data point. Or we could also drift to the cubic and cube all of the Fenthion data and use that as our outcome in the ANOVA. And so we're going to explore that more in the next question.